Welcome back. What we're going to talk about now are some key findings from lab number 2, as well as sort of overall what are some key findings and noticings you should have about position, velocity, and acceleration versus time graphs as we work now to put all of the pieces together. So let's start by talking about shape of position versus time graphs. In the previous lab, we looked at constant velocity, and so we had position versus time graphs that had constant slopes. Now we no longer have position versus time graphs that have constant slopes, because we are either increasing or decreasing the rate at which we are moving in some direction. So I have these 4 graphs, and the first thing that you want to be comfortable with is identifying with these graphs which of the 4 graphs are speeding up, which are slowing down, and which are moving in the positive direction and which are moving in the negative direction. So first let's talk about direction. How from these 4 graphs do we indicate direction? Direction, remember, comes from the sign of the slope. In your notes, it's really important to make separate sections for these 3 graphs because the big challenge with these 3 types of graphs, position, velocity, and acceleration, is that if we're not recognizing which of the 3 it is, we will mix up what the sign of the slope, for example, tells us. In this case, it tells us about the direction of motion. So we look for 2 positive slopes, even if they're increasing or decreasing, and that would be this one here is positive and this one here is positive. So both of those have motion in the positive direction, even if they are doing something different, whereas the top right and the bottom left have motion in the negative direction. So then what we want to think about is what is happening to this motion. Are we speeding up or are we slowing down? Speeding up occurs when we have a slope that is becoming steeper, regardless of sign. Right? So steeper means we start out more horizontal and we are becoming steeper and steeper with the slope. So speeding up would be this top left graph, and speeding up would be this bottom left graph, because again we're going from a less steep to a more steep slope. Whereas the other 2 here are slowing down as we go to a more horizontal slope. But one is slowing down while moving in the negative direction, and one is slowing down while moving in the positive direction. All right, so those are our findings for position versus time graphs. And now we can take a look at these 4 graphs of velocity versus time. So this graph here is all of these. Just imagine here that there are these labels for velocity versus time. And it's a good idea, if you don't already, to have these 4 in your graph, in your notes, because these 4 graphs are really important for you to know. Generally, for problems with motion, these 4 graphs here will make up part of more complex problems. So, for example, we might have a graph that looks like this bottom left graph where we start with this motion and then maybe it keeps going. Or maybe it goes back down into that 4th quadrant. Really depends. But understanding how this graph works, and then notice the 4th quadrant is this top right graph. What do they indicate? So for the top left graph, right, we start at a velocity of 0 and we are becoming more positive. So we are speeding up. But notice that this is not the same look as the position versus time graph, where speeding up in the positive direction look like this. We have a quadratic graph here, right, an x squared shape, whereas we have a linear shape here. So we go from a quadratic to a linear. And as we explore calculus later on in the fall, starting in September, you'll see why these are connected in that way. But for now, make a note of the fact that the position versus time graph has this parabola with this quadratic equation, right? Whereas when we go to velocity, we now have this linear constant slope. So anytime we go from a smaller absolute value to a bigger absolute value, the magnitude is getting bigger, we are speeding up. So that would be the same thing here. Right, I'm going from 0 to a greater number in the negative direction, so I'm speeding up. So I would have a position versus time graph that would look like that to some degree. So the other ones where I slow down, what you want to remember for velocity time graphs is to slow down, imagine you're driving your car. Your speed value is going to go closer to 0. So as I start at some positive value here or some negative value here, I head then towards 0 and I slow down. But then, for example, in this bottom left graph, if I were to then have the graph continue, I would now be having a larger number in the positive direction, and so now I go from slowing down to speeding up in this section. And that's how things are often combined. The big thing to note here for speeding up versus slowing down is something to do with the sign of the velocity and the sign of the slope. Because the slope is the change in velocity per some change in time, we can say that the slope is the average acceleration. So remember, anytime we use these delta symbols and we talk over long periods of time, we're talking about average, which happens to be the same as the acceleration at all instants because the slope here is constant. And this kinematics that we talk about is when we have motion with constant acceleration. Later on, we'll talk about a variety of different topics throughout the year where the acceleration is not constant, and that's another motivation for learning calculus. For now, the acceleration will remain constant during different segments. So this slope here is positive, and the value for so we'll say it has a positive acceleration, and the value for the velocity is positive. So when both of these are positive, we speed up. Notice for the second graph that we said was speeding up, we have a negative slope, so we have a negative acceleration, and we have a negative velocity. So as a result, these two signs are the same. We have speeding up. In contrast, when we have a negative slope with a positive velocity, or we have a positive slope with a did I say positive velocity? I hope it did. Positive velocity with negative slope, we have opposite signs. Or we have a negative velocity with a positive acceleration, a positive slope. When these signs are opposite, this is when we slow down. So slow down is when these signs are opposite. Speed up is when these signs are the same. Because remember, signs are direction. If I have a car and the car is moving to the right, if the acceleration is to the right as well, I'm speeding up because my change in velocity is to the right. Whereas if I hit the brakes and my acceleration is back the other way, I am now slowing down because these are opposite in sign. Given that discussion, let's talk now about what the acceleration versus time graphs would look like. So remember, the position versus time graph for this first graph looked like this, right? That was the position. The velocity then is this linear slope where it's like x to the first, this was x to the second. And then the acceleration being the slope. If the slope here is some constant positive value all the way from earlier up to later, then my acceleration versus time graph, ignore the spikes I'm getting, that's an error with my computer, would be some constant positive value. I have the same thing for this graph. So notice an acceleration versus time graph cannot tell me whether I am speeding up or slowing down by itself. If I just looked at these two graphs, I really don't know whether I'm speeding up or slowing down. I just know that the velocity is changing. Same thing over here. Both of these velocity versus time graphs have these negative acceleration values that are constant, but one shows speeding up motion, whereas the other shows slowing down motion. If I just had the acceleration versus time graph, I would not know whether I'm speeding up or slowing down. Let's talk about how we connect the three graphs. If we start with a position versus time graph, let's say it's that speeding up graph. How I move to the next graph is by calculating the slope. The slope gives me the average velocity for some time period, and I go from having a quadratic equation to a linear equation. So the slope gives me V average, which is equal to the change in position over the change in time. Then for my velocity versus time graph, to go from the velocity versus time graph to the next graph, again I take the slope. This time the slope gives me the average acceleration, and the average acceleration is coming from the change in velocity, right, the change in y, divided by the change in x, which is time. The acceleration versus time graph is then constant. A question you might have, or a thing at least we should touch on, is how do we go back the other way? So to go back the other way, what you want to think of is taking one of these equations, let's say taking this acceleration equation, and what if I did average acceleration times time interval rather than change in velocity divided by time? So on the right-hand side, I'd be left with this change in velocity. What I would be doing is multiplying the a value, which is here, with the delta t interval, which would be here. When I multiply a height times a base, I would obtain the area of this rectangle. You see how multiplying this height by that base would give me that area? Ooh, let's go back. That area is what we call one of two things, either the integral, or often in math you call it the antiderivative. What it means, think of anti as sort of the opposite. What we're doing is going in the reverse path. So if the slope took us from the velocity time graph to the acceleration time graph, then taking the area of this graph is what gets us back to the previous graph by giving us the change in velocity. And if I take the area of this graph, which would be a triangle, right? So in this case I do 1/2 times v final minus v initial, right? That would be the height, if we called this a final velocity, and multiply it by a change in time, then that would give me the area. And this 1/2 v final minus v initial is v average. So I'm multiplying time times v average, and that gives me the change in position, which could help me go back the other way to this previous graph. So that's how these three graphs are all connected. Slopes take you from position to velocity to acceleration. Area takes you back from acceleration to velocity to position, with one important caveat. So let's talk about the limitations of these graphs next. A position versus time graph. What can we determine? So let's say we have a little different graph this time. Let's say we have a graph like that. We can determine a few important things from this graph. First, we can determine what is our starting position, and for any time interval, what is our end position. I can also find the average velocity, so this v average, remember, is the change in position in some amount of time. So I would take a point, maybe right here where I was at the origin, and some point later, and imagine drawing a secant line. And this secant line here, if I do the change in y, right, the rise, divided by the change in x, or the run, that would give me the average velocity. What I don't have directly from this is the acceleration. What I also don't have directly from this is a way to find the velocity at any one time. That would require having calculus. And we would take the slope at one single spot, which would require an equation for this parabola. And we'll talk about that later. So the three things that you want for now are these three things. We can also describe the direction we're moving, whether we're speeding up, slowing down, or moving at a constant rate. And make sure that your notes have examples of all those things. What would imply constant versus speeding up versus slowing down? For velocity versus time graphs, what can we determine? Let's talk about that next. So a few things to start out with. First, we can determine the direction of motion. That, this time, is not the slope of the graph, but the sign. Is this negative? Then I'm moving in the negative direction. Is the value of velocity positive? Then I'm moving in the positive direction. So for this first segment of motion here, where I have negative velocity values, I would be moving in the negative direction but slowing down. Then I cross into the positive region, so I would be moving in the positive direction. I can also figure out the start velocity and the end velocity, right? And if we put these together, then we can have another piece we can find, which is the average acceleration, which would be the change in velocity in some change in time. That's a very helpful tool. Now, for all of these graphs for 1D kinematics, we always assume that the acceleration is constant. So the average acceleration turns out to be the acceleration at all times. We can also find the displacement. Remember that that is the area, and we'll talk more about that in our next lesson. And we could also find the distance by remembering that distance, this lowercase d, is equal to the absolute value of the displacement for different segments. There are some limitations to this graph, though, that are important to highlight. The first and primary limitation that we want to remember, the thing that we cannot tell from just this graph, is the starting position. So what is our starting position? We don't know. And if we aren't given a starting position, then the other thing we can't determine is what is our final position. The only way we can find those is if we have one of them. Because we can find our displacement, we can find how far we traveled, but I don't know where it is that I started, and then therefore I don't know where I end. So when we talk about being able to go forwards through graphs and then backwards on the previous page, the one thing that going backwards does make us lack is what is our starting position. And that's something you'll talk a lot about in calculus when you take integrals, that you always have to include a factor for that initial position. If we don't know it, then we would just write that we had some initial position x0. If we do know it, then we can substitute that information in as we work through problems. And you'll see that more as we do our practice. Let's talk now about acceleration versus time graph. Acceleration versus time graphs don't give us a lot of information for now until we work more through units like forces. For now, an acceleration versus time graph can tell me the direction of my acceleration. Generally, as I said in kinematics, the acceleration will be constant, so we aren't really concerned about the slope of the acceleration. The slope is actually called the jerk. I don't really know why, but that would be how is the acceleration changing. The thing we can use in acceleration versus time graph, besides finding the direction of the acceleration, is to find the change in velocity. Remember we talked about going back to the velocity time graph. The change in velocity would be the area from the line of this graph to the x-axis. So I could find how much my velocity changes. But remember, the thing that we cannot tell from this graph is what was v initial, and we cannot tell what is v final. If I'm not given that information, this graph is lacking. Therefore, if we look at these three graphs, the one that gives us the most information is the velocity versus time graph. And what we'll work through in the next video is how the velocity versus time graph should always be your primary tool. It's the piece in the middle that can let you go to the acceleration time graph or to the position time graph, and therefore we can say things about the velocity, the position, and the acceleration. It is the most useful of all of the tools. What we're going to do now is a series of practice problems here to help make sure that you're identifying all of the key things that you should know. My suggestion for you is every time I show a new problem, pause the video and think through it yourself. I'm not going to leave too much of a gap between reading and answering, so that way the video doesn't end up too long, but it's important that you try it and think through it first before seeing the answer. That way you really identify, did you know it or did you not? If you didn't know it, that's a good indication that you should take more notes on that question. So we're given a position versus time graph. We're asked what is the acceleration versus time graph. So to be able to find the acceleration versus time graph, the first thing I want to do is find the velocity versus time graph. I have a negative position graph, so I'm a negative slope, to the position time graph, so I must be moving in the negative direction, and that slope is increasing, so I need to be moving in the negative direction and speeding up. So that means I need a negative slope, and that would be graph A. All right, let's take a look at velocity versus time graphs here. We have a data point at a value of 0 meters per second. Question is, at this 2 second interval, what does this communicate? So what this communicates to us is that our velocity value is 0. The common mistaken answer choice would be A, that I'm at the 0 meter mark, but that would have to be a position versus time graph, not a velocity versus time graph. So on a velocity versus time graph, I don't know where I am without more information. I just know my velocity. All right, now with the same graph, I have another data point at 2 meters per second. What does this communicate? So answer choice A, at 3 seconds I'm moving at 2 meters per second. Yeah, that's true. At that time, that's how fast I'm moving. At 3 seconds, I am at 2 meters. That we don't know, right? Because, again, we don't know what's our starting position. So we could find how far we moved, but we don't know where we started. The next one, we've moved 2 meters in 3 seconds. Well, let's think about that for a moment, right? So I started at 0 meters per second, and then my graph would look something like that. But the thing is, we really don't know what the acceleration is. The graph could look like this, could look like that. Let's just assume that we have a linear acceleration, so it would be like this. Remember, we said that the area gives us the displacement. So the area, it would be a triangle, which is 1/2 times the base, which is from 2 to 3 seconds, that's 1 second, times the height, which is 2 meters per second. So 1/2 times 1 is 1/2, right? Times 2 is 1 meter. So I have moved 1 meter. So I can't have moved 2 meters. It can't be this one. And I didn't move 2 meters in 1 second, so that's not true either. The only thing then that is true is that I'm moving at 2 meters per second. So now we have a velocity versus time graph. What does this show? What sort of motion would we need? So the first option is one that's often chosen that would be a mistake. For a velocity versus time graph, I'm not standing still because my velocity is not 0. So answer A would be correct if this was a position versus time graph. Now the question is, am I walking away or towards the origin? Answer, we don't know. Remember that this graph does not show us what the initial position is. So I don't know. This is showing that I'm moving with positive velocity. But I don't know if that means I'd be moving towards the origin or away from the origin. I also don't know, I have no basis of comparison whether that would be running or walking. So this is sort of a trick question, but it helps to highlight a few things. Without more information, we just don't know. Here's a question to check your recall. Which of these graphs shows moving at a slow constant speed in the negative direction? So first let's talk about negative direction. I would need to have a negative velocity. So B and C are eliminated. I'm then told that after saying this negative direction, that I'm moving at a constant rate. Constant means I cannot have a changing velocity, so that leaves D and E. For slow, D has a value closer to 0 than E, so D would have a slower velocity. The answer would be D. Another one to test recall. Now we're talking about a fast constant speed in the negative direction. So working through the same reasoning as before, the only one that shows constant speed in the negative direction would be D and E, right? But D is slower, so we are left with E. Now we want one that shows a constant rate in the positive direction. Which of these shows us speeding up at a constant rate in the positive direction? So D is the first trick. D would be if this was a position versus time graph, then I would be speeding up at a constant rate in the positive direction. So it is not D. I need to be moving in the positive direction, and so C starts in the negative direction. That can't be correct, and E as well. So we're left with A and B. For a velocity versus time graph, to speed up, I need to go from a lower magnitude number to a greater magnitude number. So the only one that does that is A. Now we want one that is slowing at a constant rate in the negative direction. So this time we want to be moving in the negative direction. And so looking at these graphs, the ones that have negative direction would be A, C, D, and E. We can eliminate B. Now we need something showing a slowing down. So the value needs to become less negative. It needs to go towards 0. So that can't be A, can't be C. We're left with D and E. Constant rate means a constant slope. I'm looking for a constant slope, and the only one that has that, is E. Last one. We have a constantly, we want an object, this is a little bit of a tricky one, speeding up at a constantly increasing rate while moving in the negative direction. So first we're looking for negative direction. That's not A. That is not, that's all the others. Okay, after that we need to be speeding up. So the value needs to be going not towards 0 but away from 0. So that eliminates D. And we want the rate to increase as well, meaning we're going to get a steeper slope. So the only thing that has a negative value that is going away from 0, that is becoming steeper, is C. Okay, now for this graph, which is a really important graph because it puts multiple pieces together. What is the correct description for this graph? So talking about moving at a constant speed for A and B would be a mistake. That would be if you're thinking about a position versus time graph. I can't have a constant speed because I start at some negative value. Let's say it's -5, and I'm going towards a value of 0 for my velocity. So I must be going from a greater magnitude to lesser magnitude number. I am slowing down. So anything that says constant or speeding up would be eliminated. So we can eliminate 4 out of the 5, and we're left with E. So we slow down in the negative direction, and then we turn around and speed up in the positive direction as we go from 0 to greater and greater positive values. What about this one? What does this one show? Remember, for a velocity versus time graph, the value is what's indicating whether we are speeding up or slowing down. So if I start at a more positive value and go to a lesser positive value, I can't have a constant speed. Anything that mentions constant speed is out. As I go to 0, I must be slowing down. So the question then is, which direction am I moving while slowing down? And I'm moving in the positive direction. So negative direction is out. After I slow down, I now go from a lesser positive value to a greater positive value. So I am now speeding up. And it can look like I'm speeding up in a different direction, but the whole time my value is positive. I'm above the x-axis. So I must be speeding up in the positive direction. All right, let's talk about units for a moment here. It's important to know what the units are for acceleration. So change in velocity. Remember that velocity has units of meters per second, and then time has units of seconds. So if we take meters per second, let's try that without the error there, meters per second, and we divide it by seconds. It's really important to remember that this does not make seconds cancel out, because remember that dividing is the equivalent to multiplying by the reciprocal. So we have meters and then divided by seconds times seconds. So that whole quantity of seconds times seconds, or meters per second, which we generally write as meters per seconds squared. So this is indicating that we are measuring how much does our meters per second rate change per second. That would be our units for acceleration. Final check here. What information can we determine from an acceleration versus time graph? Remember, an acceleration versus time graph can only let us go back one step, and even then it's with limited information. So all we can find for a velocity versus time graph is with this area, what is our change in velocity? So that means I could have a change in velocity that looks like this, or I could have the same sort of change in velocity like this, because the slope value for all of those is the same, as long as they're parallel lines. So I don't really know what is the sign of the displacement, because that would be 2 steps back. I don't know the sign of the position. That would be another 2 steps back, right? The only thing I know would be the sign of the change in velocity, and if I had numbers, I could find the value for that change in velocity too. All right, so the next practice is for you working through position, velocity, acceleration versus time graphs. The book also talks about dot diagrams. Try to see if you can understand the reading. If not, don't worry too much. We're going to go over that when school starts, but it's a topic I'm going to save for when we're together in class. Thank you very much for watching, and I hope you have a great rest of your day.